Professor Collins, Bill Collins, huge ensembles of weather extremes using the Fourier forecasting neural network, FourCastNet. And I remember that the seminar will be recorded and posted on YouTube, that you can raise your hand to ask a question, a virtual hand, of course, or use the chat to say hi. I will give also a few words about William Collins. He is an internationally recognized expert in climate modeling and climate change science. His personal research concerns the interactions among greenhouse gases and aerosols, the coupled climate system, and global environmental changes, all things that are very important nowadays. Dr. Collins is a fellow of the American Association for the Advancement of Science, AAAS, the American Physical Society, the American Geophysical Union, and the American Meteorological Society. He was awarded the A.G. Tyndall History of Global Environmental Change Lectureship in 2019. He was a lead author of the fourth assessment of the Intergovernmental Panel on Climate Change, for which the IPCC was awarded the 27 Nobel Peace Prize. And also served as lead author on the fifth and sixth assessment. His role as chief scientist in launching the Department of Energy's Accelerated Climate Model for Energy program was awarded the U.S. Department of Energy Secretary's Achievement Award on May 7 of 2015. Before joining Berkeley and Berkeley Lab, Dr. Collins was a senior scientist at the National Center for Atmospheric Research and served as chair of the Scientific Steering Committee for the DOE-NSF Community Climate System Model Project. Dr. Collins received his undergraduate degree in physics from Princeton University and earned a Master of Science and PhD in astronomy and astrophysics at the University of Chicago. Bill, the floor is yours, and you're very eager to hear your talk.
Thank you, Luca, for that very warm welcome, and good morning and good afternoon, good evening, everyone. Let me share my screen, and we'll start the talk. Good, so let me just verify, can all of you see the first slide?
Yeah, I can see, we can see the first slide.
Excellent, thank you. So I'm really pleased with the opportunity to present work that we are doing jointly between Berkeley Lab and NVIDIA to look at weather extremes using a tool that's been developed by NVIDIA called the Fourier Forecasting Neural Network. And the plan for today's talk is I'm going to explain why we want to do this and why I think that this particular application of machine learning is sort of, in some sense, indispensable for studying these extremes. I'll contrast traditional numerical weather prediction with data-driven forecasting, which is what this effort is really looking to exploit. Talk a little bit about the FourCastNet model and then talk about the future, where we plan for this work to go. This collaboration is relatively young, so in several cases, I'll be describing work that's in the future. We are making steady headway here, and in fact, immediately after speaking with you today, I'm talking to the team at NVIDIA, so this is a very live collaboration. So we just concluded the sixth assessment of the Intergovernmental Panel on Climate Change. That was published electronically in 2021 and just was published physically this year. And the IPCC concluded that the future of currents of these low likelihood, high impact events, is associated with relatively low confidence. We don't really know when and where they're going to strike. We can't exclude them. They include a lot of phenomena that have pretty severe impacts on both human society and on the natural environment, including phenomena like heat waves, atmospheric rivers, tropical cyclones and extratropical cyclones, downpours and so forth. And the challenge is that precisely because they are low likelihood, it's very hard to study them in the historical climate record. In other words, we don't have good statistics on them. These low likelihood, high impact events are starting to emerge though as the climate gets warmer. We had a particularly severe heat wave in the Pacific Northwest of the United States in 2021. It was so severe that it broke a type of statistics that we use to study these events known as generalized extreme value theory, or GEV. We couldn't even calibrate GEV against the historical record to successfully predict this heat wave. It was so extreme. In other words, there were no analogs against which to form a statistical model for it. And similarly, this year, at the beginning of this year, California was both blessed and cursed with a series of extreme atmospheric rivers. These broke the drought that we had been experiencing for several years, but they were severe enough to trigger both a statewide and then a federal emergency declaration by President Biden, and have brought back lakes that have been gone for decades. In fact, one that now encompasses an Air Force base that has been turned into essentially a wading pool in the central part of California. So we're seeing these extremes emerge more and more frequently, and we need to be able to predict their impact on the natural and the built environment. The question then is, how do we do this? And the IPCC, in its language and its summary for policymakers, said that there's the probability of these events will likely increase with higher global warming levels, and there is high confidence, at least associated with that statement. So even though they're very rare now, we will see them more and more frequently as the climate gets warmer. And there are a variety of reasons traceable to the very basic physics of the climate system, why we think that the probabilities will increase, driven in some cases by very fundamental thermodynamics. So the tools that we have used to study these events and understand their causes in the historical climate record have been based up until recently on tools related to climate forecasting, and the models that we use, the numerical models that we use for weather forecasting and for climate, are cousins scientifically. Both sets of models are solving the Euler equations for shallow water on a sphere. So they're solving the Navier-Stokes equations that govern mass conservation, and then coupling those with the first law of thermodynamics and a state equation for the fluid in question. Those models have been incredibly successful in both forecasting weather on timescales of up to a couple of weeks, and also in interpreting the last several decades of the climate record. The challenge is that they are, because they're solving the underlying physical equations, they're also somewhat slow, and they consume a huge amount of computational resources, and we have them running 24 hours a day, 7 days a week to make these forecasts. So what they look like, for those of you who are not familiar with these models, is a discretization of the partial differential equations of the governing Euler equations. So they're turned into algebraic systems discretized onto a sphere. And they frequently involve not only the basic prognostic variables of the mass, momentum, and temperature of the Earth's atmosphere, but also hundreds of diagnostic variables, for things like rainfall, for example. And running them is an incredibly expensive enterprise. This shows you, for example, the compute system that's used by the European Centre for Medium Range Forecasting in Reading in the UK. And there are similar systems deployed all across Europe dedicated to numerical weather prediction. Some of the biggest supercomputers in the public domain in Europe are in fact devoted to solving NWP. And the challenge that's shown schematically on the left is one where we have a set of governing equations and a set of state. We have a state of the system. That state is constrained using a process known as assimilation, where that state is adjusted so that it looks as much as possible like observations. And then the equations are evolved forward in time beyond the present to comprise a prediction of the future state of the weather system, and that's what's shown inside the circle on the right of the diagram. And that spread, that sort of gray circle, is the forecast uncertainty. And then the diamond is the resulting forecast that shows up on your iPhones, for example. What we are doing as part of this effort with NVIDIA is imagining doing much the same problem, but orders of magnitude faster, and with orders of magnitude more members of the ensemble. So we can look at the tails, extremely rare events that comprise the tails of a distribution subject to forecast uncertainty. NWP models, as shown in this diagram, typically run 10 to 20 different perturbed initial condition instantiations of the climate to sort of encompass uncertainty and run them into the future. As I'll come back to in a moment, we're going to put that whole problem effectively on computational steroids. So the NWP community has been making remarkable progress. This shows its history over the last 3.5 decades. We now have forecasts that have considerable fidelity at 10-day timescale. The limit of predictability has been established at about 14 days. This has been known since the work by Ed Lorenz, a meteorologist at MIT, who was, of course, one of the people who created the Lorenz system and first understood the presence of chaos in simplified representations of the Euler equations. So 14 days is essentially the limit for the growing modes that govern the chaos of the system to sort of wreck memory of the initial conditions. But in the face of that uncertainty, the numerical weather prediction has been making remarkable progress over this time. So this is really a testament to the success of that community. The challenge for that community, however, remains, and it's been steady for a long time. Weather involves looking at length scales across roughly 8 orders of magnitude, and the diagram on the left shows you that range of length scale and also time scales from seconds up to centuries. And the corresponding set of models that work on these problems are shown on the right, with pardon me for all the different acronyms there, but essentially we've constructed models that, a set of models that work across that range of scales, but you'll notice that no one single model can do them all. We have to rely on a hierarchy of models. And the challenge is that many of the severe systems that we want to study, these low likelihood, high impact events, are at length and time scales that are shorter and quicker than we can readily treat with existing NWP models. And so there's a scale gap, both in space and time, between the models that we use for numerical weather prediction and the really severe storms that we need to be able to predict in order to safeguard our resilience and the resilience of our natural environment around us. That said, the computer industry has been making great strides. So this shows you the computing power at the Geophysical Fluid Dynamics Laboratory at Princeton, and one of the 2 winners of the Nobel Prize in 2021. One of the 3, pardon me, Nobel Prize winners, Suki Minabe, was a scientist at GFDL and was using computers that are back in the 1960s on this diagram. These computers are considerably less powerful than the chips in your cell phones by a couple of orders of magnitude. Nonetheless, using the computers of the day, Suki was able to make some of the most basic discoveries about the dynamics of the climate system. So it's a testament with what you can do with a little bit of computing power. Fast forward to today, we've increased computing power by literally 1 trillion relative to the computers that Suki Minabe used for his Nobel Prize. And in the United States, we are fortunate to have a set of systems deployed by the Department of Energy. One of them is sitting just downhill from me. It's a computer called Perlmutter. It runs at about 100 petaflops per second. There's a sister system to it that's at the Swiss Meteor, and is being used by Swiss Meteor for their numerical weather prediction. We have 2 more machines that have exceeded an exaflop. One of them is running at Oak Ridge. It's called Frontier, and the second machine, called Aurora, is being assembled now at the Argonne National Laboratory. And I'm using the work that I'm going to show you shortly is being done on Perlmutter, and the enabling capability that's really making it possible for us to pull off these remarkable strides going beyond traditional numerical weather prediction is the use of graphical processing units, or GPUs, in all three of these computers and the machine at Swiss Medio. So, I mentioned the evolution of resolution the requirements for resolution that I needed to get down to the smallest phenomena. This shows you the evolution of resolution in climate models used in the IPCC. So the acronyms here are FAR, SAR, and TAR, the first, second, and third assessment reports. AR4 is the fourth assessment report that was issued in 2007. In the most recent reports, we've been getting down to about 30-kilometer resolution that's shown on the right. So you can really see the difference this makes to being able to resolve the orography of Europe. Makes a tremendous difference. You can actually see the Pyrenees, see the Alps, and so forth. And of course, the Greenland ice sheet, which you couldn't in the crudest models that were used in the very first climate predictions. But still, let me just remind you that even 30 kilometers is not adequate to look at some of the phenomena that we need to resolve for low likelihood, high impact extremes. So, is there an alternative to NWP? And the answer is yes. So another way to go would be to use data-driven weather prediction. And this is something where we essentially use the data produced by an NWP to train a machine learning algorithm. We have a long record that now extends over about 40 years, going back to the dawn of the satellite era. So that's 15,000 days worth of data that we can use to train these machine learning algorithms. And what's remarkable is that the team at NVIDIA, with whom we are collaborating in 2 years with roughly 20 people, has stood up one of these models. And that's an order, so that's 40-person years to stand up one of these models. Contrast that to what I estimate to be 1 to 2 person millennia of time to construct a traditional Earth system model for the IPCC. So it's an order and a half magnitude faster than traditional NWP or climate modeling in terms of being able to construct a model quickly. And as I'll illustrate during this talk, it's gaining skill at a really remarkable rate. Let me start by illustrating how quickly it's gaining resolution on an NWP. So this is a short history of resolution of these data-driven weather prediction models. And starting on the lower left and working up to FourCastNet, which is running at 1/4 of a degree resolution. So only 5 years ago, those models were covering the planet with a 60 by 30 grid that comprised 1,800 pixels. And now we're up to 1 million pixels effectively, or grid points covering the planet. That's a gain of 500 in just 5 years. In the same time period, NWP has gained a factor of 4. So over the same time period, these data-driven weather prediction models have gained 100 times as much resolution as NWP. And again, this gives you a sense of how rapidly these models are evolving. FourCastNet is really pushing this concept of digital twins. And in fact, NVIDIA is collaborating closely with Destiny and other efforts in Europe to build digital twins. And the plans are to deploy these capabilities in concert with one another. So it is a surrogate of the Earth's atmosphere. Its heart is a neural operator combined with a Fourier transform. And the Fourier transform, as I'll come back to a little bit later, is really an essential characteristic of why it's both so fast and can gain resolution so quickly. It's being trained off of an analysis of the historical climate record from the European Center for Medium Range Forecasting. ERA5 is an acronym for a reanalysis of the past several decades of the Earth's climate system. It can make an inference of the climate system in half a second. That's a 2-week forecast out to the limit of predictability. And so its speed up relative to numerical weather prediction is somewhere between a factor of 10 to 100,000. And it saves a factor of 10,000 in power consumption making that prediction. So you can again see these remarkable orders of magnitude gain relative to traditional models from these machine learning and artificial intelligence algorithms. And now, as the stable rollout there, these slides are dated at a remarkable clip. That stable rollout is now out of date. The longest, the model is stable out to at least a decade now. So add another 0 to that stable rollout number that's at the second lowest bullet on this slide. And what it's being trained on is a set of variables that govern the state of the Earth's atmosphere. So these are the surface wind and temperature and surface pressure fields, and then wind fields aloft, another field known as geopotential height, and then total integrated water vapor. And of course, it's trained on a portion of the climate record and then validated on portions of the data that we withheld. Why did I get interested in this system? So the challenge that we face is that we want to study events that recur so infrequently that there may be only one instance of them in 100 to 150 year long climate record. So, for example, if I wanted you to look at a 500-year flood, that means I have to rely on highly uncertain written records, not digital records, but written records from people alive at the time 5 centuries ago. And if we really want to understand, look at the statistics of these events, written records of that kind are not going to be sufficient. So the only way to produce a sufficient number of realizations is via simulation. And essentially, to use the fact that the climate system can be treated as an ergodic system, so we'd essentially trade time for copies. And the idea is that if we create a large number of parallel Earths with slightly different initial conditions, and then let the chaos of the system push each of those into a different state in a timescale of a couple of weeks, we can scan across that ensemble of many copies of Earth as a means of essentially spanning centuries of time. And so it's the ergodicity of the system that really is the enabling. So we can trade copies for time is really the key here. And it was when I realized this, it was why I became convinced that FourCastNet and other models of its kind are exceptionally viable for characterizing rare climate extremes. And so the proposal, and this is the thing that we are currently working on NVIDIA to realize, is to generate huge ensembles with 10 to the n members, where n might be on the order of 4, required to converge statistics. So if we had, 10 to the 4, 10 to the 5 copies running over, let's say 10 to the 4 copies running over 4 decades, that's equivalent to simulating 400,000 years worth of Earth's climate history, more than enough to get great statistics on these low likelihood high impact events. And so for this reason, I'm convinced that FourCastNet is essentially, and models of its kind, are essentially a killer app for studying this kind of problem. There are open scientific issues that we're still exploring with the NVIDIA team, and we've been working closely with them on sort of working through whether or not FourCastNet is actually properly simulating the onset of chaos, whether or not it actually does exhibit ergodicity and so forth. And those are tests that we are applying with some considerable rigor with them as we get this project up and running. Let me show you a few of the properties of FourCastNet in terms of what it's capable of doing. So this is the surface wind field from FourCastNet on the upper row and the reanalysis on the lower row over the United States in meters per second. It shows you how the model is able to really capture patterns of frontal systems propagating over the United States, some considerable fidelity out to lead times of 3 days or so. And to reproduce the fine scale structure of these frontal systems with some considerable fidelity. It's also able to simulate cyclones, and so this is again showing you in the surface wind field being generated by, in this case, a typhoon on the left, and then several tropical these are tropical cyclones, Florence, Isaac, and Helene on the right. In the lower diagram, you can see labeled. And the comparison here is, as you can see in each of these dotted diagrams between FourCastNet and ERI5, the FourCastNet is able to accurately capture the structure of the wind fields, both around the typhoons and cyclones, and also the wind field downstream and upstream of these systems. And the team at NVIDIA has also been looking at its ability to look at the landfall of hurricanes onto the United States. This particular hurricane is Hurricane Michael, and again, remarkable fidelity between FourCastNet and the reanalysis. This movie, if it's going to, yes, it is running, is showing you a phenomenon that's particularly relevant to the Western United States, which are atmospheric rivers. These bring a third of the potable water to California, and so recharge the snowpack in the Rockies, which supplies water to about 1/10 of the U.S. population. It's really vital for us to be able to predict the evolution of these atmospheric rivers, and the FourCastNet has extremely good anomaly correlation scores that look comparable to those in NWP up to 1.5 weeks. And I'm going to show you some of those anomaly correlation scores in just a moment. I'll skip this. One of the other one of the phenomena that we are particularly interested in my group is extreme rainfall. And this is this work actually is some nice results from a collaboration between NVIDIA and some scientists working here at the National Energy Research Supercomputing Center, or NERSC, the place where Perlmutter is located. One of the challenges that we face with these models is they diagnose precipitation, and they don't produce precipitation, as shown on the left, that's as extreme as the underlying reanalysis. So the diagram on the left shows you ERA5, which we regard as ground truth, in terms of the percentile of the rainfall event. So 0.01% of rainfall events on this diagram have total precipitation in a day that exceeds 50 millimeters. That's where the dashed black line intersects the right hindmost axis. And FourCastNet tends, if we only train it and don't compensate its tendency to smooth at small length scales, it tends to underpredict those severe rainfall events. So my colleagues here at NERSC have coupled FourCastNet to a generalized adversarial network and trained it to produce the smallest scales at which we observe really severe rainfall events. And once they've added that adversarial loss function, they're able to bring the rainfall predictions from FourCastNet inside the uncertainty bound from ERA5, which is a very nice accomplishment. It means we can predict exceptionally rare and strong rainfall events. And this just sort of shows you graphically what happens. The picture of the globe with South America in the lower diagram with an 18-hour lead time is from the model where we have not done this correction. And if you compare it with the ground truth in the upper left, you can see that it's been smoothed at the shortest length scales. And once we add the adversarial training, we get an 18-hour prediction in the upper right that has the fine scale structure that we actually observe in the storms propagating over the Amazon basin, and also in the intertropical convergence zone out of the Atlantic into the Pacific to the west of South America. So this shows you that we can recover fine scale features in these models required to really emulate the most extreme rainfall. And so the team at NVIDIA is now, has begun thinking through with sort of modest size ensembles this question around predicting the future from initial conditions. This is an example of their work looking at Hurricane Florence. And they've also begun thinking through the question about whether or not one could deploy this same capability on looking at the future. And I've been collaborating with them on using results from the 6th IPCC assessment to test the proposition about whether or not we could use FourCastNet to make long-range predictions. By long range, I mean centennial in length. And there's another collaborator of the team at NVIDIA being led by Chris Brotherton out of Seattle, Washington. That's in fact looking at the question of whether or not we could use FourCastNet to replace climate models, or at least emulate climate models for making predictions of global warming for the end of the 21st century and beyond. And that work is ongoing, but Chris and his team have made great strides in doing so. So one of the tests, one of the key questions so far, I've been showing you sort of illustrative eye candy, but the hardcore way that these models are evaluated is to use the same metrics that are used by NWP centers to test the fidelity of their NWP models. And we've adopted the same tests and applied them to FourCastNet and compared the results of those tests to the NWP models that were used to train FourCastNet. So the diagram, ACC stands for anomaly correlation coefficient, and it's a metric of weather scale. If it's 1, it means the prediction exactly corresponds to what was actually observed when the prediction ended. Once we wait long enough to get to that, make the future the present. So a score of 1 means the model had a perfect prediction. And as you can see, that the anomaly correlation coefficient tends to decay with time because of the onset of chaos and loss of skill. IFS is an acronym for the Integrated Forecast System. It's the sister to, another system being run by the European Center for Meteor Range Forecasting. It has a higher anomaly correlation coefficient than FourCastNet, but the two, in fact, overlap in their uncertainty bounds. And this is shown both for this geopotential height, which is a variable that governs basically is an indicia of high and low pressure systems that govern synoptic scale weather, as well as 10 meter surface wind shown on the right. So when we use the same metrics that are being used by NWP centers, FourCastNet is doing remarkably well. The other thing that one wants from these systems is that the ensemble of perturbed initial conditions, realizations of the climate system, they sort of, as you evolve them forward in time, that the spread across the ensemble grows with time. And the idea here is that you want an ensemble that can encompass, at least in some of its, as edge cases, black swan events. So the idea, the fact that this ensemble with, ever so slightly perturbed initial conditions, that the members start to differ from one another is a feature. It's a highly desirable feature of weather forecasting, because you want to make sure that if one of the 10 members predicts a really strong storm, that you encompass that in your weather predictions. And as shown here from a comparison of FourCastNet against the European Center for Meteor Range Forecast, the FourCastNet is doing a remarkably good job of growing spread at the same rate as the underlying numerical weather prediction models. And this again is a measure of spread for the 500 hectopascal geopotential height, again an indicator of high and low pressure systems. And I will skip this diagram. It's essentially making the same point. One of the other remarkable properties of the system, and this is really a game changer, and this is a diagram thanks to Bjorn Stevens at the Max Planck Institute for Meteorology in Hamburg. this model, because it's so fast, is going to be a complete game changer in terms of the way that we handle data in both the climate and numerical weather prediction communities. And the reason why is that it's actually cheaper to rerun the model from scratch than it is to save the data from it. In other words, if you want to, for the purposes of reproducibility, what we've always done in the climate community is we've saved the output from our simulations of future climate, because those simulations are exceptionally expensive. They require allocations of billions of CPU hours to conduct something like the archive that was constructed for the 6th IPCC assessment and produce 40 petabytes worth of output. And the reason why we save all that data is, again, we don't want to go back and again expend billions of CPU hours. What this diagram shows is that one needn't do that. In fact, you could save a snapshot of the evolving of these NWP models, and then essentially train a numerical weather one of these FourCastNet models or another data-driven weather prediction model at the snapshot, and then reproduce the time in between these snapshots at no cost. So numerical weather prediction models and numerical weather prediction centers may get into the habit of just saving instantaneous snapshots that have been used to initialize data-driven weather prediction models to recreate the historical record. We can also imagine doing this with climate models. And so the era of needing titanic amounts of data storage and expending huge amounts of energy and data storage resources on archiving the very precious output from climate models and numerical weather prediction models, that may soon be an historical artifact, simply because it's fast and cheap to reproduce these runs using these data-driven weather prediction emulators. The last thing I'll just mention, and this is the point I was making earlier, is that the FourCastNet, when I first met the developers in this group a year ago, they were able to run their models stably out to 5 days. They're now out to roughly 4,000 days. So they've gained, in the space again of just a year, they've gained a factor of 1,000 in the length of simulation they can run over which their model is numerically stable. And so again, this gives you a sort of a sense of how rapid the gains have been in this community. I will close, and then, in the interest of leaving plenty of time for questions, I want to spend a little bit of time on computational performance and talk about why both the indicia of the exceptional performance of this model and also where it comes from. So one of the features that you want in a highly performant numerical model is a metric known as strong scaling. And I'm sure all of you know what that means, but just in the interest of making sure, strong scaling is a property of a model where if you allocate more computational resources to a problem of the same size, its performance, in other words, throughput, scales with the number of computing resources being allocated to it. And weak scaling is the sort of a different condition where the only way to get high performance as you increase the number of resources available to a model is to make the problem bigger. And traditional numerical weather prediction and climate models are very typically in the latter category. They exhibit weak scaling. So if you give them more compute resources, because there's so much communication overhead and such a large memory bottleneck in those models, you have to make the problem bigger. You can't take by way of contrast, FourCastNet exhibits spectacular strong scaling. And that's what's shown in these diagrams. This is a model with a fixed size on 3 different computers. So the computer names are Joules, Perlmutter, and Selene. And you can see the number of GPUs being allocated. These are log graphs, and the rate of the number of samples per second being generated on these machines by samples, I mean inferences. And on all three computers, the model is exhibiting superb strong scaling. So that's a really desirable property and a very distinguishing feature of it relative to classical NWP and climate models. The other remarkable feature of this model, and something that I think will be very important for its deployment, is that it can be trained really rapidly. So those of you who do machine learning know that the training is as opposed to inference, is by far the most expensive part of getting a model up and running. My own group has found, and this graph illustrates, that we can retrain these models on years worth of data in under a wall clock day. Now, the reason why that's important is that if it turns out that if we, for example, want to run these models in parallel with traditional numerical weather prediction, and in fact, if, say, the European Center wanted, or another center wanted to run a model like FourCastNet in parallel with their own NWP model in order to inflate the size of their ensemble, they have the luxury, and in fact, they can easily retrain the model on the latest, climatic conditions inside a weather prediction cycle of one wall clock day, because the training occurs sufficiently quickly. And that's another remarkable property of this model. It guarantees that it can sort of evolve with evolving conditions. If the training needs to evolve with evolving background state of the climate system, that is certainly possible. Now, the reason why all this is enabled is the underlying Fourier operator inside the implementation of FourCastNet. And in essence, what's happening is that the system is being trained effectively to emulate a Green's function for the climate system. And the Fourier operator shows up in an application of the Fourier convolution theorem. And because of the use of Fourier techniques, the FourCastNet model scales like the number of grid points. For NWP, by number of grid points, I mean in a latitude or longitude direction. NWP scales like the number of grid points in the latitude or longitude direction cubed. And the reason is that the grid is going quadratically, like the number of points in the latitude and longitude directions, plus an additional factor that's due to the current Friedrich-Levy stability condition on the time step. And that requires the time step to get shorter as the resolution increases. So NWP, if you want to increase the resolution by a factor of 2 spatially in both latitude and longitude directions, requires 8 times, let's say 10 times as much compute power. FourCastNet only requires twice as much compute power. And again, this is a distinguishing characteristic between FourCastNet and NWP. What it means is that the only reason why we cannot run this model at length scale, say, of not 25 kilometers, where it's currently operating, but at 1 kilometer, is that it's memory limitations, and quite literally, we don't have the data to train it. We've sort of the model is so performant that it's actually we're going to have to wait until the NWP community catches up with it in order to have data to train it against. So that's really quite a remarkable statement about the capabilities of this system. And I'll skip this. Let me close with this some final thoughts, and then I'll be delighted to take your questions. As I mentioned, when I first started talking to the group at NVIDIA, they were operating at weather timescales, and weather timescales are hours to weeks. And as I mentioned, the limit of predictability from the work of Ed Lorenz and others is at 2-week timescales because of the onset of chaos. Curiously, the timescale at which climate sort of starts is also roughly 2 weeks. And the reason is that climate is governed by a coupling between rainfall in the Earth's atmosphere and the flow of radiant energy, sunlight and infrared energy through the Earth's atmosphere. those two things are coupled with something called radiative convective equilibrium. And it essentially, the heat released by the formation of rainfall offsets the loss of heat to space from the radiative transfer of infrared energy from the Earth out into the vacuum of deep space. So those two things balance each other. And the timescale for that equilibrium to come into play is also 2 weeks. So weather ends at 2 weeks and climate starts at 2 weeks and then extends off to the right on this axis. FourCastNet is now able to scale this range of phenomena from weather up to climate, which is really powerful enabling capability. And it allows us now to range over short-range forecasts where we need to be concerned about things like hurricanes making landfall, all the way out to thinking about the seasonal outlook, the El Nino oscillation in the Pacific Ocean, thinking about decadal scale climate change. This one model can now span this entire time scale and can be decision relevant, as shown in these various applications: emergency management, deployment of energy resources, certainly in the American West, thinking through planning for water. We have to plan for droughts on 5-year timescales. This system can now span a wide range of very useful applications. So what I've indicated to you is that this model has really excellent skill, and we've been testing it using the same metrics used by NWP centers. We can generate huge ensembles in seconds. It's much faster than NWP, and also is greener. It has a much smaller energy footprint. We're looking ahead to some very interesting possibilities, possibly extending it to the whole Earth system, not just to the atmosphere, going to even higher resolutions. Thinking through how to possibly even beginning to couple it to data assimilation, but that's in the future. What my group and I are wrestling with now with NVIDIA is how to, our goal is to go back and look at some particularly unusual years in the climate record recently and ask, what are the extremes that could have been that we just barely missed? So that's the project that I have underway. And in 7 minutes' time, I'll be talking to my colleagues in NVIDIA about that precise problem. So with that, I'd like to thank the team at NVIDIA and also at several other universities, Purdue, University of Illinois. I'd like to especially thank the two individuals pictured on the right. Mike Pritchard, who's sort of spending time at NVIDIA on leave from the University of California, Irvine. And was the person with whom I first talked about starting a collaboration. And especially my grad student, Anka Mahesh, shown in the upper right, who's been working with me on the collaboration with NVIDIA. It's really been an incredibly fun project. And I look forward now to taking any questions that you might have. Thank you so much. So let's start the Q&A, please. And I'm going to stop sharing.
Thank you. Very impressive talk, and I think we have already a few questions from the Q&A. So I will read them so that also other people can listen to them. You mentioned extreme events several times. How do you determine extreme rainfall, temperature, and flood events, for example? So. What is an extreme event? That is probably the question.
Yeah, there are two definitions of that. One of them is sort of practical in nature. Does the event cause significant damage that takes time to recover from? I tend to look at this more statistically, and therefore think about them as being events that occur that are 3 sigma away from the median or more.
Okay.
So yeah, I can read the second question. I can read the second question, Luca, if you wish. The question is, the FourCastNet model looks great, but I noticed that the standard reference for it is still this preprint. And I'm sorry to say that some of the comparisons in that document did not impress me. Is there going to be a standard peer-reviewed reference for this model? The answer to that question is yes. So I had a team of 5 people working on a variety of different metrics for that model that we developed in conjunction with the European Center. The model is quite performant relative to those. Ankur and I are writing these up and do plan to submit those to the peer-reviewed literature. Mohammed, I do appreciate the spirit behind this question. And yeah, I think I only want to use this model if the people who've been doing this work for decades concur that it exhibits sufficient fidelity to actually be useful scientifically. So I agree with the spirit of your question, and I do think that it's we've been in that spirit. We've developed a metrics package, given it back to the NVIDIA team. I've applied it to FourCastNet and plan to publish on that this fall. Thank you for that question. Oh, and Dave, sorry, I see it's actually you, not Mohammed. But thank you. Other questions for me?
Okay. No, from the Q&A. I don't know if somebody wants to it can also probably switch on the microphone and make the question live if somebody wants. My question, I have a curiosity because it's I've just been surprised, but it's probably because I know very little about the climate modeling. It was my impression that really climate was very difficult to predict because of the chaotic nature and the difficulty in making long prediction. Now you're talking, if I understood well, of 90 days prediction or even more. How is that possible? I mean, what is behind? Probably is because the fluctuation somehow eventually are compensate, and you are able to make prediction of expected values quite accurately.
It's precisely, we're making predictions of expected values, Luca, not a deterministic prediction, right? And one of the reasons why the climate is predictable at timescales like several months is that the thermal equilibrium timescale of the ocean is on the order of 15 years. So the ocean is acting essentially as a heat bath, and the atmosphere is coupled to the ocean. So all the thermal inertia of the ocean acts as a very stable lower boundary condition on the behavior of the atmospheric fluid. So that's one reason why the system is not, doesn't exhibit or is as predictable as it is. The other boundary condition, of course, that's highly predictable is the upper boundary condition, the seasonal cycle of solar insolation. So both the lower and the upper boundary conditions, are on the fluid are very stable on long time scales, right? And that constrains the behavior of the fluid in between. So that's one of the reasons why the system is predictable in terms of expected values on timescales of months to years. Excellent question. Thank you.
Thank you. If there are no other questions, here there is a question of the Q&A. You highlighted the need of training data, the gold standard of which being reanalysis. You mentioned the need for improved training data to come from improved physical models, higher grid and process resolution. Isn't true, therefore, that the need of vastly improve our capability to develop physical models and the method are prerequisite to enable better training data?
Yes, we will. The NWP community continues to advance the skill of the models and also to push them to higher and higher resolutions, and that's an incredibly viable enterprise. I think Europe is leading the way here with the thoughts about creating this destiny or digital twin of the Earth running at 1 kilometer resolution that's being constrained with data assimilation. So once Destiny comes online, we can train FourCastNet against it, and that'll be a remarkable capability once that vision is realized. Europe is in the process of procuring 3 of the world's largest supercomputers. One of them, in fact, just got stood up in Finland, and there are 2 more on the way to realize this vision of Destiny, this digital twin of the Earth. So I completely concur with the spirit of this question, and we look forward to working with our colleagues in Europe on seeing, the utility and realizing the utility of Destiny as a training data set for data-driven numerical weather prediction models of this kind. With that,
so for me, that I'm more a physical model of people, there's still hope to have our job.
Yeah, very much agreed. Well, Luca and company, I very much thank you for your attention, and very much appreciate the invitation to be part of your series. And I wish everyone a very happy holiday season. I now need to go talk to my NVIDIA colleagues. So all the best as you wrap up this year. And I look forward to seeing you at a conference sometime soon.